Today we're doing a deep dive into the movement of heat. We're at the Chenmai factory in China, which is the largest producer of vapor chambers in the world. And they're giving us a tour.
Vapor chambers spread out heat unreasonably quickly. They boil water at 30 degrees Celsius, condense it back into a liquid on the other side to release its latent heat energy, and then transport the water back to the processor without any moving parts. It's really cool stuff, and they're absolutely essential for cooling down the ever more powerful chipsets inside our smartphone. There are a million small details that make it work, and to really understand vapor chambers, I'll show you the different ways heat can move, how vapor chambers work, how they are made.
There's actually quite a few more steps than I thought.
And how they are actually implemented into a device like this, and explain every little detail along the way. There is no sponsor segment in this video, even though Oppo sponsored it. Practically the only talking points they gave me is to explain vapor chambers and show them in action in their new phone Reno 14. I wish I had more sponsors like that. Alright, hot. The best way to move heat is as follows. And the funniest thing is that I'm dead serious. This is called advection. It's when you move the properties of something, like thermal energy, because you move the thing itself. And it sounds so incredibly stupid and dumb, right? But it's actually really common. You see, when you have an air cooler, you don't wait for the air to cool down. No, you just move it out of the way and then you get some fresh air. And then the hot air does its own little thing, right? It expands a little so it becomes lighter, and then it rises, then it mixes with cool air. That's called convection. But that's really just something that air and water do. It's not really its own type of heat movement. The second way heat can move is through conduction. Temperature is just the average kinetic energy of a bunch of atoms or molecules. Something is hot whenever its particles are moving fast, and when one pushes into the next, the heat can move through a material. That's conduction. Metals are generally really good at that because their atoms are tightly connected. Gases, on the other hand, are quite bad heat conductors because they have about 1,000 times less particles for any given volume. So there isn't a whole lot of kinetic energy, and molecules in a gas aren't connected at all, so they have to bounce into each other. But as I said, there's not that many molecules in a gas, so bouncing into each other can take quite a while. Relatively, of course. The interface layer between a metal and a gas is also very interesting. When there's no gas molecules to bounce away, the kinetic energy of the metal atom is just returned back into the material because the atom is held in place. This is also why a vacuum can be an excellent insulator. A thermos actually uses this technique. It's a double metal wall with a vacuum in between. So the metal on the inside cannot conduct its energy to the outside because there's no molecules in between. We'll ignore the third way heat can move in this video, which is electromagnetic radiation, basically light, because our whole goal is to prevent things from getting so hot that they start to radiate a significant amount of their thermal energy. So we are left with advection and conduction, and well, moving the processor doesn't really help to cool it down, so we need to look at conduction first. But conduction has a big problem. This is one of the quality control stations in the factory, and here they do a thermal camera test. On the left station there's a regular piece of metal that will only conduct the heat, because I took a vapor chamber and destroyed it with a knife.
Destroyed.
It will later become clear why a hole like that keeps it from working. And on the right is a working vapor chamber.
Yeah. Pretty clear.
Underneath is a heating element that simulates the processor of the phone. They have some tape on top so that the reflective metal doesn't mess with the temperature readings of the thermal camera. As you can see, pure heat conduction doesn't do a great job. That's because heat only moves from hot to cold. And the bigger the difference, the more heat moves. If two parts have the same temperature, the heat doesn't move at all. So you will always need significantly hotter parts and colder parts on your device if you just use conduction. But in order to get rid of the heat to the outside air, we want to spread the heat out as evenly as possible over the outside of the device.
So we have the broken one and the good one. Let me show you what happens if I blow on it.
The vapor chamber cools down way more than the heat conductor simply because the heat is better spread out over a larger surface area. So how does a vapor chamber do that? Well, the first step is to boil water at 30 degrees Celsius, which is weird, right? As you might know, the boiling point of water depends on the pressure around it. On top of the Mount Everest, it would be just 70 degrees, while in a pressure cooker, it can get up to 120 degrees. So by pulling a vacuum in the vapor chamber, they carefully tune the boiling point of the water inside to make sure that it starts boiling early enough to keep the processor cool, but that it still condenses back into a liquid at ambient temperatures. Making such a thin vacuum chamber that doesn't collapse in on itself is quite a challenge.
The material comes in on these big rolls, and before it goes to the actual stamping press, they make sure that's the right thickness, which is 40 microns.
That's thinner than a piece of paper. They use stainless steel because it's much stronger than copper and a bit lighter, which allows the vapor chamber to be thinner and lighter too. In fact, it's just 0.32 millimeters thick. That's crazy.
In the actual press, they move forward a little bit at a time. So first they cut out this part, then they cut out that part, then they make the holes, something like that.
They're actually taking out the die so we can have a look.
And there's actually quite a few more steps than I thought, and a lot more detail. So here you can see a little dovetail.
But it's on the outside, so it doesn't actually make it into the final product. And something similar for these dots on the corner. They get cut off, so I'm curious what they're for.
If you know, leave a comment.
This is coming with me.
Here's the dimple plate, and here some last minute changes to make sure it pops out again. Very cool.
After stamping, you end up with one of the outsides of the shell of the vapor chamber. The other side is much the same, but it's just flat. These dimples keep the halves separated so it doesn't collapse under the pressure of the outside air. They're a bit like pillars under a structure so the roof doesn't collapse. When the water is evaporated, it needs to condense and then come back down again to be transported to the hotspot again. And for this transportation, they treat the metal. The machine is sadly secret, but they clean the metal and then they create a thin oxide layer on top. This keeps it from reacting with the water inside, but more importantly, it lowers the contact angle of the water. You might have noticed that water droplets sometimes bead up, while other times they spread out. You can quantify that with the angle at which the edge of a droplet hits the surface of a specific material. This is used as a measure of how attracted that material and water are to each other. It's very important for vapor chambers to be hydrophilic, to attract water, because the next step is to add a wick that moves around the water inside of the vapor chamber.
This is where it all comes together. They take the two stamped outer shells and they put a little wire mesh in between.
It's a very fine stainless steel piece of woven fabric. It comes in on these 100-meter rolls. They cut it with a laser and then laser weld it to the bottom plate, and then they weld on the top plate, of course. The wick works as follows. Some materials can pull water up against gravity. That's called wicking or capillary action. And it's a combination of surface tension and the water contact angle. The water contact angle below 90 degrees makes the sides jump up a little against the wall. And if you then have two of these walls close by, you get a U. And you can imagine that the surface tension tries to pull it straight. And then the contact angle tries to become low again. And then the surface tension tries to pull it straight, etc., etc. And of course, this happens at the same time, but you get what I'm saying. It really feels like a cartoon character that flies by pulling itself up. But somehow this is the reality that we live in. It works better and better the closer the walls are to each other. It's freaking beautiful. And this is what happens between the mesh and the bottom plate. Because of the wicking, these things work in all directions. They don't really have a bottom or a top, but this is how I will show them throughout the video, so bottom and top. One fun detail is that you might think that the wick would wick on its own, but without the bottom plate, it doesn't actually do anything. It needs the plate to act as a second wall, and then it works like a charm.
This machine looks the same to you, but this is where they actually finish it. The first step is to degas it to check for leaks. Then they put water inside, then they degas again, and then they boil the water for a little bit to make sure that all the air and other non-condensable gases are outside, and then they laser it shut and cut off the end part.
It's filled with straight up H2O, by the way, just pure water, no need for any weird or toxic liquids. And then the final manufacturing step, with all the stamping and laser welding, stresses can be created or released in the material, warping it a little bit. So
this is a flattening machine, which does exactly what you think it does. It flattens the vapor chambers, and that helps with connectivity and mounting and that kind of stuff.
And that's one vapor chamber practically done. But one big question remains. Why do they work so well? I mean, there's only about one drop of water water inside of this. And wicking is not really a fast process. So how in the world does this tiny little bit of water transport so much energy? And the answer is latent heat. I told you that temperature is the average kinetic energy of molecules, right? Well, you can convert it to a different type of energy for a little bit and then release it again as thermal energy later. Say that these two marbles are water molecules and this round ditch is their bond. They can move, but you need quite some energy to break that bond, which is what happens in evaporation. In fact, heating up water from 0 to 100 degrees takes just 20% of the energy that you need to take that same water at 100 degrees and evaporate it. And this percentage difference is especially steep when you only need to go from an ambient temperature of, let's say, 20 degrees to a boiling point of 30 degrees. This evaporation step really takes an insane amount of thermal energy out of the system. It's really cool stuff. Okay, so then you have a gas and it's hot and moving fast. The marble is not going back in, it just jumps over the ditch. The water vapor stays a vapor, but when it cools down and it slows down again, it can fall back into the ditch and it gains momentum by doing so. Hence, water vapor releases its latent heat energy when it snaps back into its liquid bond, heating up the surrounding molecules. The vapor chambers still need to get checked. Every single one of them. There is a heating element and two temperature probes, one right above the heating element and one on the other side of the vapor chamber, and they look at the difference between the two thermometers, and if the difference is larger than just 5 degrees, they throw it out.
This is a printer on which they print a QR code on every single part. QR codes were actually invented in factories like this to keep track of every single part. So if anything goes wrong, you can trace it back to the individual tool head if you need to.
After that, they're finally ready to be mounted into the phones. Let's take a look inside. This is interesting. I'm always surprised that phones are basically just a battery. Hey.
Here we see the chipset with thermal compound on top and some thermal pads for the smaller chips to make up some height. The vapor chamber is located behind the battery, between the battery and the screen. Let's take a look from the other side. I don't open phones on the regular, so not only did I break the screen, I also had no idea what this shiny flexible sheet inside the screen was. But if we put it under a microscope, we see that it's actually the screen itself. Here it is on a working phone. These dark parts are letters.
Yeah, there we are. Haha, the vapor chamber. I believe it's the biggest currently on the market of this thickness.
These black sheets you see all over the phone are also a type of thermal pad, but made from graphite. Graphite has a somewhat similar performance as silicone thermal pads through the thickness of the material, but along the pad it's about 100 times better. So it doesn't just connect two surfaces, but it also spreads the heat between them.
So they start out with this stuff.
It's some kind of polymer. They stack it up in towers with some graphite plates in between and bake it to get rid of everything that isn't carbon. Then you get something like this.
This is very brittle.
Then they sinter it. They put it in a furnace that bakes it for 5 full days, up to 3000 degrees Celsius. After that, they press it onto a piece of plastic and you get one of these graphite sheets.
And that's also what we see here, but with an adhesive.
Let's see how this vapor chamber performs in the real world. iPhone 16 on the left versus Reno 14 on the right. Both of them are running the same stress test. The iPhone doesn't have a vapor chamber and it has a bad hotspot and it started to overheat and throttle down its performance after just 1 minute. So it wasn't really able to take advantage of its more expensive chip.
Now, in the last few years, these vapor chambers have become quite a bit larger, thinner and better tuned, not to mention a lot cheaper. But where is the technology headed and what are they currently working on? Foldable phones are a big question mark for the industry, of course, so everyone is probably working on a flexible vapor chamber in the background somewhere. They're also trying to eliminate the wick. I mean, if you can get rid of it, you get rid of a third of the parts. Heat pipes have the same working principle as vapor chambers, but they generally have a sintered powder on the inside as the wick. And you can imagine that you might be able to do something like that, but then very thin as an oxidation step, for example. But one of my favorite improvements that they're working on is as follows. The water on the top layer needs to go down again. Currently they have a hydrophilic coating to decrease the water angle so that these pillars transport it down. But in between the pillars, droplets can get larger and sometimes reach for the wick on their own.
Why not treat it to make the water angle higher so it touches the wick earlier? 希望它能够在尾部形成
Yeah.
缩水结构。
It's a very good question. We have some study.
By coating the top with a hydrophobic material and increasing the contact angle, droplets can actually reach the wick earlier. So you can imagine that there are some other interesting tricks you can do by changing out hydrophilic or hydrophobic coatings on different parts. One of the things they added in the highest trim of the Reno 14 series is aluminum oxide nanoparticles in the water to help with nucleation. When water transitions to a gas, it needs to start somewhere. In a kettle, you can often see a lot of bubbles start in a very specific spot. That's because there is an easy starting point for the water to transition to a gas. Often it's a small crevice in which a tiny bit of gas is trapped, so the water on the edge can transition into a gas as well. And then a bubble forms, but the gas in the crevice is left behind to do it again. Well, by adding these aluminum nanoparticles to the water, nucleation can be a bit better apparently. Aluminum oxide is also a very good heat conductor, so well, this is one of the things they are working on.
Thanks to Oppo for sponsoring this video. Thanks to Chiang Mai for showing us around in the factory. You hear my voice is kaput. I hope to see you in the next video. That should be it. I'm done.